Picture this. A sleepy observatory pulls an all-nighter, stacks a few glittery frames of the sky, and whispers to the world that an interstellar traveler named 3I/Atlas just blinked and nudged its path. Internet headlines pop like popcorn, comment sections do their aerobic workout, and you and I are left with the cosmic equivalent of a skid mark. Did it really swerve, or did we just catch it at a weird angle while our planet was jogging around the sun and our instruments were still wiping the sleep from their eyes? Welcome to the cold open. No spoilers yet, but by the end of this episode, you will know why a tiny kink in a streak of pixels can mean either steam puff science or story fuel for the boldest what-if minds. Earth is basically a rock that won the cosmic lottery, and sometimes the prize is front row seats to a mystery. Let us set the tone. When astronomers say something changed course, they are not picturing a driver cranking a wheel. Space does not do dramatic lane changes on a whim. What they mean is that the predicted line drawn from earlier measurements no longer hugs the newcomer's latest positions quite as snugly as expected. Imagine you track a gull across the beach by the footprints it leaves in the sand. You sketch the path forward, and then the next set of prints appears a little to one side. Did the gull take a playful sidestep? Did the wind ruffle the sand? Or were your first footprints misread in the glare? That is the tension right here. Signal, system, or something stranger. First, the sober science promise. We will walk through how tiny pushes can nudge icy visitors. We will talk about how perceiving a curve on the sky can be an illusion born from our moving vantage point. We will peel back the curtain on instruments, software, and the subtly treacherous business of turning dim points of light into trajectories. No equations, no chalk dust, no secret handshake. Think of this series as a friendly telescope tour where the guide sticks around to answer the awkward questions. Space is not offended by awkward questions. It is basically one giant shrug in vacuum. Now, the equal and opposite promise. We will let the imagination off its leash, but only after we clip on the collar of evidence. Speculation is the seasoning, not the stew. What if a piece of interstellar hardware was surfing sunlight like a sail? What if a tumbling shard of something engineered was testing how patient human astronomers are? We will try on those ideas the way you try on sunglasses at the airport gift shop. Curious, playful, and ready to put them back if the fit is wrong. Black holes are the universe's way of saying delete browsing history permanently. Engineered probes would be the universe's way of saying we read it first. Either way, we will ask for receipts. Here is what makes this particular rumor irresistible. We have seen interstellar visitors before, and each one dragged a suitcase full of questions. Some looked like comets that forgot to RSVP. Some brightened and dimmed like stage lights obeying a moody director. So when a fresh object shows up and the early dots refuse to line up cleanly, our pattern-loving brains perk up. We love a twist. But if the cosmos has a theme, it is that twists tend to hide inside details. A faint puff of gas here, a jitter in the star map there, a subtle change in the way sunlight shoves on dust. The difference between it swerved and we misread it can be smaller than a human hair held at arm's length. Space mysteries are often solved with a ruler, a nap, and another night of data. There is also the drama of timing. Early observations are like meeting someone at a crowded party and trying to guess their life story from 2 sentences and a half smile. The first nights matter, but they are also the messiest. You fight glare, haze, quirks of each camera, and the fact that Earth is cruising along its own track while you aim. If the object is faint, if the images are noisy, if a bright star photobombs the frame, the path you sketch can lean a little. Later, with more dots stretched across more sky, the line straightens, and yesterday's eyebrow raise becomes today's shrug. The universe did not change. Your confidence did. Still, we should not smother the spark of what if under a blanket of caution. The reason we build telescopes, publish alerts, and talk out loud about anomalies is that nature occasionally surprises us on the first take. A jet of gas can kick at just the right moment to look like a pilot tap. A chunk can flake off and pivot the whole body a whisper to one side. A dust fan can flare into view like confetti from a shy party cannon. Photosynthesis is plants' way of saying we invented solar panels first. Comets are rubble piles that say we invented steam rockets by accident. If 3I/Atlas really twitched, the culprit could be humble and still thrilling. So here is our pact for the series. We will treat every headline like a clue and every measurement like a character with motives. We will let doubt be a co-host and curiosity hold the mic. We will explore the natural toolkit that can masquerade as steering, then dare to sketch a world where steering is real and deliberate. If the story narrows to ordinary physics, that is not a letdown. Ordinary physics in an interstellar traveler is like finding a familiar heartbeat in a stranger. It tells us we are connected, that the same playbook works far from home. And if the evidence ever tilts toward engineered behavior, we will not jump to melodrama. We will ask for multiple, independent signatures that refuse to be anything else. We will weigh the noise and the bias, and the temptation to see faces in clouds. We will keep the jokes, because science without a grin is just a meeting. But we will keep the rigor too, because wonder without discipline is just a daydream. For now, hold the headline gently. Changed course may be the universe doing what it always does, or it may be the beginning of a chapter we have never read. Either way, we are here for the story, and the story starts with getting to know our visitor without borrowing trouble. Next up, we will pull the curtain on who 3I/Atlas is, where it came from, and why a traveler from between the stars can make even seasoned astronomers sound like kids in a planetarium. Chapter 2, Meet 3I/Atlas, the new visitor. Before we chase rumors of swerves, let us meet the traveler. Interstellar objects are drifters that were born around some distant star, then flung out by gravity drama and left to wander the galactic neighborhood. Most comets and asteroids we know are family. They loop the sun like regulars who know the barista by name. Interstellar visitors are strangers who step through the door, scan the menu, and do not speak the language. They arrive fast, stay briefly, and keep going. Our planet is that lucky stone that hit the jackpot, and every so often, the prize is a flyby from a tourist who did not get the memo about staying home. 3I/Atlas is our newest guest in that category. The 3I tag means it is the third interstellar object confirmed by the community, and Atlas credits the survey that spotted it. Think of the naming as a mailing label, third piece of off-world mail, delivered by the telescope network with the catchy acronym. It is not a personality test, but the moniker does hint that we are living in a new era where wide sky cameras sweep the heavens night after night and catch surprises that would have slipped by only a decade ago. How does 3I/Atlas compare to earlier visitors? 1I/ʻOumuamua was the shocker that looked more like an asteroid than a comet and brightened in odd ways. 2I/Borisov was much more like a classic comet, a fuzzy snowball with a tail, as if to say, relax, I am exactly what you expected from deep space. 3I/Atlas arrives with its own blend of clues, its speed relative to the sun, its angle of approach, and its early brightness pattern paint a portrait that is neither a carbon copy of ʻOumuamua nor a repeat of Borisov. The fun part is that each interstellar visitor is a lottery ticket with different numbers. We learn not by forcing them into a single mold, but by letting each one tell its own story. Why do these travelers whip astronomers into high alert, like baristas on triple espresso who just heard a bus of customers pull up? Because interstellar objects are time capsules. Their surfaces were shaped by a completely different star's nursery and a different rhythm of planet building. When sunlight warms their skins, the gases and dust that escape are chemical postcards from places we have not yet visited. Even their shapes and spins carry history. A collision long ago, a slow bake near a faint star, a tidal stretch during a close pass with a giant planet far away. They are not just rocks, they are biographies in motion. 3I/Atlas carries extra intrigue because each new member of this tiny club helps answer a huge question. How common is the tossing out of building blocks from alien solar systems? If 3 interstellar visitors have wandered through our yard in the short span of modern sky surveys, then the galaxy might be littered with these drifters. That matters for more than curiosity. It feeds models of planet formation, clues for how often planets migrate, and even practical dreams of someday sampling alien dirt without leaving our system. Imagine a future mission snagging grains from a passerby, the way a kid sticks out a hand for confetti during a parade. What can we say about the physical nature of 3I/Atlas without spoiling later chapters? We can say that brightness over time gives hints about size and reflectivity. If it is rough and dark, it has to be larger to shine the same amount as a compact, pale object. Color, when measured through different filters, whispers something about the mix of ices and dust on the surface. The rate at which that brightness flickers can signal a spin or a lopsided shape. All of these are first impressions, like reading a face in a crowd. They are not courtroom proof, but they help the scientific community aim its most precious resource, time, on the best instruments. The path 3I/Atlas takes through our neighborhood is also part of its biography. An interstellar visitor arrives on a long, open arc, not a closed loop. It dives past the sun and then sails outward for good, shaped by gravity, but not bound by it. That path means we have a narrow window to collect information before the guest is gone for good. There is a theater curtain quality to this. The stage lights turn on, the scene plays out, the curtain falls, and that act never repeats. Astronomers plan like stage managers, hustling telescopes to the right vantage points before the show moves on. There is poetry in the idea that our first solid samples from other star systems might not come from starships, but from dust that drifts into our reach. Each new interstellar object is a practice round for that dream. 3/Atlas teaches us where to look, how quickly to organize, and which questions matter most when time is short. It trains the reflexes of a community that is getting very good at tapping you on the shoulder and saying, "Look up now." If you listen closely to the chatter around 3I/Atlas, you hear a mix of giddiness and discipline. Giddiness, because we are watching a postcard from another stellar address streak across our sky. Discipline, because we know how easy it is to overinterpret a dim smudge on a changing backdrop. The joy of this moment is that both moods are allowed. Wonder gets us to the telescope. Care keeps us honest when we interpret what we see. So consider this chapter your backstage pass. You now know what makes an interstellar object special, how this third visitor adds a fresh twist to the tale, and why professionals are buzzing with exactly the same energy you feel when a rare celestial guest appears. Our stone that hit the jackpot gets to study travelers that took the long road here. Next, we trade romance for rigor and show how those dim dots become a path we can predict and test, one careful measurement at a time. Chapter 3. How we know where it is. Orbit fitting 101. Let us turn the lights up on the detective work. When astronomers figure out where a faint traveler is headed, they do not lasso it. They take pictures. Each image marks the guest as a tiny dot among thousands of stars that behave like a fixed wallpaper. One dot moves night by night. The wallpaper stays put. From that humble start, a trajectory is born, not by chasing the object across the sky, but by crunching the positions into a path our eyes might not believe, until the math insists. Observatories do not follow the comet. They follow the numbers that grow from patient measurements. The craft is called astrometry, which is a fancy way of saying, measure the where and when with care. A telescope takes an exposure. Software maps the stars in that frame to a trusted sky catalog. like overlaying a grid with known landmarks. That lets the team translate the moving dot's pixel position into a location on the celestial sphere with a timestamp. Do this again tomorrow and the next night, and suddenly you have breadcrumbs. Each crumb is a data point with uncertainty bars that say, "We are pretty sure it is here," give or take a tiny margin. Now the fitting begins. Imagine throwing a handful of magnets on a whiteboard and trying to lay a smooth ribbon through them that best represents their overall line. You want a single ribbon that hugs the crumbs without bending into silly loops, just to pass through every speck of noise. The method behind the curtain weighs all the points and looks for the path that minimizes the collective misfit. In plain words, it finds the story that explains all the sightings with the fewest winces. This story is not a guess. It is a disciplined compromise between imperfect measurements and the reality of motion under gravity. Early paths wobble because early crumbs are few. With only 2 or 3 positions, many ribbons can pass the test. Add a 4th and a 5th, and the family of possible paths narrows. Think of zooming out on a maze to see the exit. Each new point zooms us out a little. That is why early predictions often come with generous cones of where it might be next week. The universe is not changing its mind. Our picture is sharpening. There is a twist that can fool a casual glance. You do not live on a fixed camera. Earth is circling the sun, twisting our viewpoint like a moving dolly shot in a film. This creates parallax, a gentle apparent bend in the path that is not the object doing tricks, but your vantage point sliding sideways. The fitting process knows this and includes the motion of the observer. It has to, or else we would mistake our own motion for a cosmic swerve, which is the celestial version of thinking the train next to you is moving when it is actually you. The quality of the fit is judged by the residuals, which are the tiny differences between where the model says the object should be and where the telescope actually found it. If the residuals look random and small, you relax. If they line up in a pattern, you tighten your grip on the pencil. Patterns mean the story is missing a character. Maybe a measurement was off because a star overlapped the target in one frame. Maybe atmospheric blur smeared the dot and pulled its center slightly. Or maybe the object is experiencing a gentle push that gravity alone does not explain. You do not leap to drama. You fix what you can fix and see what remains. Different observatories help in different ways. A big, sensitive telescope can catch the object when it is faint and far, anchoring the long wings of the path. A smaller but persistent instrument can add steady nightly dots that reduce uncertainty quickly. Telescopes in different hemispheres give you different viewing angles, which is gold when the object skims low for one site and high for another. Each additional, well-calibrated measurement is like another nail in the floorboard that stops a creak. Timestamps matter as much as positions. A late clock or a misrecorded second can nudge a dot just enough to throw off the fit. That is why observatories synchronize their timing hardware and audit their pipelines. The sky gives no do-overs, so the ground has to be meticulous. Even the star catalogs used to map frames evolve, replacing older positions with improved ones. Updating a catalog is like upgrading your map from mostly right to trustworthy, and sometimes that alone straightens a mysterious kink. When the fit is healthy, it yields predictions: where to look tomorrow, how bright it might be, and which instruments can catch it best. Those predictions feed back into the observing plan, making the whole process a loop that tightens with each pass. If the object fades, you lengthen exposures. If it brightens, you shorten them to avoid smearing. If a prediction misses, you widen the search box and ask whether the model or the measurements need a tune-up. All of this may sound dry, but there is a quiet thrill to watching numbers tame a streak of night into a path you can bet a telescope on. It is a craft that rewards patience and humility. The universe rarely shouts. It leaves breadcrumbs, and the people who sweep the floor for them are the heroes of nights you will never read about in splashy headlines. The next chapter will build on this foundation, by exploring how illusions in the sky can trick even careful eyes, and why your moving viewpoint can turn a straight journey into a painted curve. Chapter 4. Sky Illusions. When course change is in your head, picture yourself on a train looking out the window. A distant mountain seems steady, a line of nearby trees rushes backward, and another train sliding by makes you briefly swear that your car is drifting the wrong way. Congratulations, you have just lived the core plot twist of celestial parallax. Now swap the train for a spinning, orbiting planet with a camera bolted to it, and that twitchy feeling becomes a graph that says the comet turned, even when the traveler is cruising straight as a ruler. Sometimes the universe is fine. It is your camera that needs a snack. Parallax is the simple mischief of seeing from more than one place. Hold a finger in front of your face and blink one eye, then the other. The finger jumps with respect to the background. Your finger did not sprint. Your vantage point switched. Now scale up the trick. Earth rotates once per day and loops the sun once per year, so your viewpoint slides constantly. If you plot a distant visitor against the starry wallpaper over several nights, that built-in slide paints gentle bends in the path. The object is not carving S-curves in space. You are the one doing the dance. There are two flavors of this dance that matter most. First, daily parallax. As Earth turns, an observer at midnight is on the side of the planet that faces one direction in space. By dawn, that same observer has rotated to a new post hundreds of leagues away. Take an image before bedtime and another near sunrise, and you are peeking from different rungs of an invisible ladder. The result is a tiny left-right nudge that gets baked into your dot-to-dot picture. Second, annual parallax. Over weeks and months, Earth's orbit shifts your whole platform along a huge track. This slow slide lends the longer arc curves that seduce headlines. The nearer the target, the larger the apparent squiggle. It is the cosmic version of nearby fence posts whipping past, while the far ridge barely moves. Here is the kicker. Tracking choices can amplify the illusion. If you lock the telescope on the stars, the interstellar traveler drifts across the frame. If you lock on the traveler's predicted motion, the stars trace arcs. Later, when you stack images to boost the signal, your software must decide which frame of reference to honor. Stack for the object, and background stars smear into graceful streaks that are not truly arcs in space, but a record of your own motion. Stack for the stars, and the traveler's path can look kinked simply because you are stitching together snapshots from a moving platform. Neither view is wrong. They are different narrators telling the same tale with different accents. Altitude adds spice. Near the horizon, you look through a thick wedge of atmosphere that refracts light, pushing images slightly toward the zenith. As an object climbs, that push relaxes. If you collect positions across a wide range of altitudes without modeling this bend, the path can inherit a slow, dignified curve that whispers steerage, even though it is just air doing what air does. On a crisp high night, this effect shrinks. On a hazy low night, it flexes. The sky is not gas station glass, but it is absolutely a lens with opinions. Now bring spacecraft into the story. A camera on a satellite near Earth, a camera parked near a stable gravitational balance point, and a camera riding along a solar orbit, all watch from different baselines. Imagine three friends filming the same parade from a balcony, a street corner, and a drone. A marching band that looks to turn sharply in the balcony footage might appear to stride straight in the drone's view. Combine these vantage points without careful geometry, and you can discover a turn that evaporates when each clip is analyzed in its own frame. Spacecraft do not magically free you from parallax. They remix it into new forms because they ride different tracks than the ground. Even timestamps, without touching instruments, can play mind games in a purely geometric way. If your measurements cluster at the same local hour each night, say always right after dusk, the vantage point shift from Earth's rotation is nearly the same between nights. That can hide a small part of the daily parallax signature. and make the longer, annual curve more dominant. Collect another sequence near dawn a week later, and boom, a fresh, offset set of points appears to nudge the path. The comet did nothing new. You changed when you looked. Perspective also fools intuition about speed. When an object's path crosses our line of sight at a shallow angle, it creeps across the sky, then appears to speed up as the geometry swings to a steeper cross angle. This is like watching a plane fly toward you, seeming to hover, then zip sideways near overhead. Plot that by eye, and you might mumble about a throttle change. Plot it with a model that accounts for the three-dimensional geometry, and you get a smooth, lawful cruise. The speed on the sky is not the same thing as the speed through space. One is a shadow on a wall, the other is the dancer. And then there is the stacking illusion inside long exposures. Suppose you take a single, very long shot while tracking the stars. The traveler draws a faint line, but if the object brightens briefly in the middle of that shot, you will see a line that looks thicker or knotted in one segment. Viewed later without context, that knot can be misread as a bobble in direction, when it was only a moment of extra glow smeared along a straight path. The universe did not hiccup. Your drawing tool laid down a heavier stroke for a heartbeat. All these illusions share one moral: geometry is a stage magician that never runs out of scarves. The fix is not to distrust your eyes, it is to move beyond them. You build models that include where and when you looked, from what platform you looked, how the air bent the light, and how the line of sight turned raw positions into a trace on the dome. Once you do, a great many cosmic swerves dissolve into smooth, elegant rails, which is not boring, it is beautiful. It means the traveler is telling a clean story, and you are finally listening in the right language. So the next time a plot of points makes your pulse jump, remember the train window. Are you watching a curve, or are you the one curving? Space is chill. We are the ones doing the waltz. Up next, we will explore the real nudges that can introduce honest wiggles, the tiny thrusters nature installs on icy visitors, and how sunlight can turn a dusty snowball into an accidental rocket. Chapter 5: Real Forces, Real Wiggles, Jets and Venting. If sky illusions are the brain's prank, jets and venting are the body's shove. Comets and many interstellar visitors are not solid billiard balls gliding politely. They are layered, lumpy, and full of volatile ices, locked inside a dusty sponge. When sunlight pours in, those ices do not melt into lakes. They skip straight to vapor, muscling through pores and cracks until they burst out as narrow fountains. Each fountain is a tiny thruster. Add enough tiny thrusters, and your quiet snowball becomes a jittery spacecraft that never read the manual. Photosynthesis is plants' way of saying we invented solar panels first. Comets say we invented steam rockets by accident. Start at the surface. Imagine a crust of dark dust blanketing brighter, fresher ice beneath. In the cold far reaches, the crust sleeps. As the object drifts inward, the sun's energy creeps down grain by grain, warming pockets of ice. Vapor forms within, pressure rises, and the gas searches for escape like steam hissing through a kettle lid. Wherever a fracture meets daylight, a jet needles outward. Because the surface is uneven, the sunlight is uneven, and the fractures are wildly uneven. The jets are a patchwork. Some fire up at dawn, some wake only in local noon, and some flare when a shadow moves aside. The object has a personality, and that personality is moody. Rotation turns this patchwork into a choreography. Picture a garden sprinkler on a slow spin, except the nozzle is a ragged cliff face, and the water flow flickers with every passing shadow. As the body turns, a jet that points one way at sunrise points a different way an hour later. That means the force on the nucleus keeps changing direction. The net result is not a clean push like a rocket stage. It is a tug, then a wobble, then another tug, all adding up over hours and days. From a distance, you see a gentle deviation from perfect gravity motion. Up close, It is a drum solo of puffs. Not all jets are born equal. Some seep quietly through porous dust, spreading into broad fans. Others blast through tight vents and travel straight for many lengths before spreading. The narrow ones carry more punch because the flow stays collimated, which is science's polite way of saying it does not give up and wander. If a pair of these narrow jets fires from opposite sides, their forces can partly cancel. If one dominates because its vent is larger or sunnier, you get a preferred shove. That preference, kept up for many turns, becomes a measurable non-gravitational acceleration, a tiny but stubborn bias in the path. Dust changes the game in two ways. First, gas drags grains along for the ride, loading the jet with mass and momentum. Second, the grains that are too heavy to escape fall back, thickening the surface blanket and choking future vents. Think of a chimney that gradually clogs itself. Sometimes the reverse happens. A patch slumps or a cliff collapses, exposing fresh ice that has not seen sunlight in ages. The next rotation, that newborn patch screams with activity, and the whole torque budget of the comet shifts like a chair scraping across a floor. There is a rhythm to the heating too. Surfaces do not warm or cool instantly. Thermal inertia delays the peak temperature until after local noon, which means the strongest jetting often comes after the point of maximum sunlight. That lag matters. Place a jet on a rotating body, add a delay between sunshine and raw, and you can systematically twist the spin or tweak the orbit in a particular direction. It is like pushing a child on a swing. The timing of the push matters more than its raw strength. Seasons exist even on these small travelers. If the spin axis tilts, one hemisphere can bask for months while the other hibernates. Active areas migrate with the seasons, turning on and off as the sun's angle changes. A region that did nothing on the way in might roar on the way out, making the object behave differently before and after closest approach. This seasonal flip can fool anyone who expects symmetry. Nature loves symmetry in theory and chaos in practice. Deep inside, the structure is a riddle box of voids, pebbles, and frozen gases. Vapor moving through that maze may find easy highways in one direction and dead ends in another. The pathways channel the flow, so vents can appear in places you would not expect from surface sunlight alone. A shadowed pit can still breathe if the plumbing connects to a sunlit reservoir. That is why mapping brightness on the skin never tells the full story. The underground is a tangle, and the jets are its exclamation points. Torque deserves its own drum roll. Every jet that fires off center twists the body a little. Over weeks, those twists can change the period of rotation, sometimes speeding it up, sometimes slowing it down. Alter the spin, and you alter which patches see morning and for how long, which then alters the pattern of jetting. This is a feedback loop, a conversation between sunlight, vapor, and spin that can drift from quiet to rowdy. In extreme cases, the spin can change enough to destabilize a fragile cliff, leading to a landslide and a sudden burst of fresh activity. The comet is both engine and engineer. From the outside, these messy local processes add up to a clean signature, a steady, small departure from the path predicted by gravity alone. It does not look like a zigzag. It looks like a whispering hand on the shoulder, persistent and patient. If you model the forces with the right shape, spin, and schedule of heating, you can reproduce the wiggle. If you ignore them, you end up accusing the universe of misbehaving when it is only your model that skipped breakfast. Do not mistake ordinary for dull. Jets and venting turn an unassuming lump into a self-modifying traveler. They write diaries in dust and vapor, revise the spin, and leave the subtlest fingerprints on the orbit that we can read from worlds away. Steam rockets by accident, indeed. In the next chapter, we will step back from the local and look at the invisible hands that never turn off, gravity's gentle edits from the sun and the planets, and how a faraway giant can still nudge a passing visitor like a bouncer with perfect timing. Chapter 6, Gravity's Fingerprints. Planetary nudge, solar tides. If jets and venting are the fussy housemates of a comet, gravity is the landlord. It says little, signs no emails, and yet every time you come home, the furniture has been moved 3 inches to the left. Gravity is the friend who never texts back, but always shows up to rearrange your furniture. For an interstellar visitor like 3I/Atlas, that quiet mover can trim or stretch the path in ways that look subtle on a plot and feel monumental in the mathematics behind it. Start with the drive-by. When a small body cruises near a planet, it does not have to clip the mountaintops to feel a tug. Planets sit inside invisible hills of influence, regions where their pull can briefly compete with the sun's. Pass through the outskirts of one of those hills, and the visitor's path is shaved like a haircut you did not ask for. The outcome depends on geometry. Arrive from ahead of the planet, and you can leave a little faster, as if you stole speed from the planet's own motion. Arrive from behind, and you can exit a little slower, handing speed back. Nobody swerves hard in the moment. It is more like a gentle lane merge that miles later means you missed an exit. The power of this nudge is all in the missed distance and the tempo of the flyby. A pass well outside any moons can still matter if the relative speed is right and the approach line points just so. Think of rolling a marble past a spinning bowl. You might not fall in, but the edge will bend your track. For comets on long arcs, even a tiny change in direction near the inner system can balloon into a large shift in where they will be years later. That is why mission designers obsess over something called the encounter plane, a page in space where you can draw the incoming path and measure how a displacement of even a few dozen miles can land you in a different future. Now widen the lens to tides. The sun's gravity does more than hold the family together. It pulls on the near side of a comet a little harder than the far side, stretching the body and its coma into a subtle teardrop. That same stretch acts on the path like a slow, persistent editor, trimming the shape of the orbit during the closed solar pass. For a loosely held rubble pile, the strain can become drama. Cliffs fatigue, crusts crack, and sometimes fragments detach. You might not see the break in a single night, but the stress is there, writing in small letters that can add up to a boldface event. Planets tug tidally too, and they do it long before the object feels like a captive. A far encounter with a giant like Jupiter can reorganize the visitor's future, as if a librarian walked past and quietly refiled your book under a different letter. Jupiter, in particular, is the bouncer of the system. Its mass is a neighborhood watch sign with implied muscle. The funny thing is, a pass that is too close can actually limit the time for the tug to act. The visitor zips through the danger zone before the full stretch develops. A slightly wider pass can be more effective for editing the trajectory because the handshake lasts longer. Resonances add their own beat to this story. If the timing of a visitor's swing around the sun matches certain repeating patterns with a planet's orbit, tiny kicks can stack. Picture a parent pushing a child on a swing. A light tap at just the right moment, again and again, sends the arc higher. For a visitor on a one-time hyperbolic dash, you do not get many kicks, but the principle still holds for deflection before and after the main act. 2 or 3 rhythmically placed nudges can be the difference between a clean exit and a path bent toward a chance future encounter. There is also the matter of gravitational focusing. The sun and the planets do not just pull. They steer incoming traffic toward themselves. Far away, a visitor might be headed for a simple miss, but as it enters the curved valley of a massive body's pull, the path is bent inward, lowering the miss distance, compared with a straight line forecast. That focusing increases the odds of a more consequential nudge and deepens the role of geometry. Arrive with a slightly different aim, and you land on a different section of the valley wall, leaving with a new heading that looks on later plots like fate. Tidal forces do not only act on the nucleus, they sculpt tails, ion tails, those blue spears that point away from the sun, trace magnetic highways in the solar wind. Dust tails, the broad pale fans, respond to gravity plus the shove of sunlight. The sun's pull curves those tails in a graceful arc that tells you, at a glance, about the speed of release and the path taken since. For an interstellar visitor, reading the tail is like glancing at a windsock at the airport. You learn the direction of the invisible flow and the edges of the runway. You might wonder how we separate a true gravitational autograph from the mess of jets, reflections, and perspective. The answer is patience and pattern. Gravitational edits are smooth and predictable once the geometry is pinned down. They do not switch on at local noon or pause when a shadow creeps across a vent. They scale with distance in a way that does not care about which face is sunlit. If you can predict the shape of the deviation months in advance by tracking where the big players will be, you are watching gravity's steady hand, not a local tantrum. Sometimes the most meaningful nudge comes from not hitting a target, but missing a small region near it, a so-called keyhole. Sail through a keyhole before a planet, and gravity will arrange for you to be in the wrong place at the wrong time, one orbit later. For short-period comets, keyholes can set up future close approaches. For an interstellar passerby, a similar concept applies as a one-shot redirection. Thread a narrow corridor, and your outbound path aims at a new slice of interstellar space. The cosmos loves a hinge moment disguised as a routine pass. In the end, gravity's fingerprints are everywhere, precisely because gravity never clocks out. It is quiet, universal, and weirdly patient. Where jets are local and seasonal, gravity is global and perennial. It does not care what the visitor is made of, or how pretty its tail is. It moves the furniture 1 inch at a time until the room is transformed. Next, we will look at another gentle chauffeur that never sleeps, the pressure of light, and the wind from the sun, a soft breath that, over long runs, can turn dust and gas into obedient dancers. Chapter 7, Sunlight Pushes 2, Radiation Pressure and Dust Drag. If gravity is the quiet landlord and jets are the fussy housemates, sunlight is the nosy neighbor who keeps nudging the mailbox as they walk by. Every beam of light carries a whisper of momentum. It is small, but it is relentless, and space has a lot of light with nowhere else to be. When that steady stream of photons pelts a dusty, gassy traveler, it does more than make the object shine. It pushes. Over hours and days, those shoves add up, gently steering the fuzz around a nucleus into elegant shapes that look like intention from far away. The solar wind is basically space weather that forgot its umbrella, and it tags along as a stream of charged particles with its own opinions about where tiny things should go. Start with the photons. A grain of dust is a miniature sail, whether it knows it or not. When light hits it, some of the light is absorbed and re-emitted as heat, and some is reflected. In either case, momentum is exchanged. The push is strongest on the tiniest grains because they present a lot of surface compared to their mass. Big chunks are stubborn. Fine powder is obedient. That is why comets grow wide, delicate dust tails that curve away from the sun. The smallest grains are swept hardest and fastest, while larger specks lag, tracing a family of graceful arcs. The tail is not a single brushstroke. It is a whole set of strokes sorted by size, each responding to the steady hand of light. Now add a twist that sounds like sci-fi, but is just patience with a poetic name, Poynting-Robertson drag. As a grain orbits the sun, it absorbs light coming slightly from the forward direction in its own moving frame and re-radiates that energy in all directions. The net effect is a tiny braking force that robs the grain of orbital energy and makes it slowly spiral inward. It is as if the grain is jogging through drizzle, and the raindrops keep tapping its chest. Not a big deal in a minute, a very big deal over months. For a cloud of dust shed by a lively visitor, this drag sorts the grains by who gives up first, changing the shape of the dust fan subtly as time passes. Gas responds differently because atoms and molecules do not wear little sails. Freshly released gas from a warm patch around a visitor heads outward in all directions, making a fuzzy coma. Sunlight does have a say here, but less through pressure and more through energy. Energetic light can knock electrons off neutral atoms, turning them into ions. Once ionized, the gas stops behaving like a sleepy perfume cloud and starts listening to the magnetic fields carried by the solar wind. That is when the second pusher enters the scene like a gusty crosswind through an open market. The solar wind streams outward from the sun, a river of charged particles braided with magnetic fields wound into a spiral by the sun's rotation. When ionized gas from the visitor meets this river, it is picked up and accelerated along those invisible rails. The result is the ion tail, that narrow, often blue-tinted spear that points almost straight away from the sun, where the dust tail is a painter's fan. The ion tail is a fencer's lunge. Kinks and disconnections sometimes ripple down this slender blade when the wind's magnetic field flips, or a shock wave passes by, like a flag snapping when a storm front arrives. Radiation pressure and solar wind do not act in isolation. They collaborate and compete. A single outburst from the nucleus can launch a mixed cloud. The smallest dust surrenders to light and swings wide. Mid-sized grains outline a curved corridor. Heavy grit hugs the path of the nucleus, dribbling along like sand from a pocket. Meanwhile, the gas becomes a multi-layered mess. Neutrals drifting in a slow balloon, ions sprinting down the magnetic highway, and exotic fragments glowing in signature colors that let spectroscopists tease out which species came from which kitchen shelf in the nucleus. Size matters, but so does shape and texture. Fluffy, porous aggregates act like overachieving sails, catching more light for their weight. Smooth, compact grains act like stoic pebbles. Composition flavors the response too. Bright, icy grains reflect more and feel a stronger photon push. Dark, carbon-rich bits soak up light and warm up, re-emitting in the infrared with a slightly different thrust pattern. Think of it as a fleet of boats on the same river. Rafts, kayaks, cargo barges, each catching wind and current in its own way. For our interstellar visitor, this dance of light and wind matters because observers fit trajectories not to a point, but to a system in motion. When telescopes measure the center of brightness, they are not necessarily measuring the center of mass. A long shimmering tail can tug the measured centroid a little off the true nucleus, especially in shorter exposures or in crowded star fields. Over several nights, that bias can mimic a slight deviation. Good pipelines correct for this by modeling the coma and tail, or by using sharp images that isolate the tiny core. The lesson is simple. Sunlight can move dust, and moving dust can move your ruler. There is a boundary layer worth a shout-out. The bow where the solar wind first senses the comet's presence and slows. In that region, ions are born in a rush. Magnetic field lines wrap around, and the whole structure becomes a tiny, temporary magnetosphere. It is not stable like a planet's, but it is real enough to deflect particles and channel flows. Sometimes this cocoon sheds a tail of its own, a detached streamer that drifts away when the wind snaps like a rubber band. Watching those moments is like reading the space weather report in real time, with the comet acting as a windsock no one had to install. All these forces leave signatures we can read. The double-tail geometry, with dust broad and curved, and ions straight and narrow. The way the dust fan changes as the visitor moves inward and outward. The occasional tail disconnection that tells of a passing shock. None of this requires an engine under the hood. It requires sunlight, magnetic fields, and time, which the solar system supplies in heroic quantities. So yes, sunlight pushes, and the wind of charged particles shoves. And together, they sculpt a traveler's shroud into shapes that look like personality. That is not illusion. It is physics with a flair for drama. Next, we will pivot from the fuzzy outskirts to the stubborn core and talk about spin, how an irregular body tumbles, how torques from jets and sunlight twist that tumble, and why steady is a bedtime story small worlds almost never tell. Chapter 8: Spin Doctors. Tumbling nuclei and chaotic torques. Take a potato, carve it into a lopsided brick, and throw it into the air. It does not spin like a ballerina. It flops like a shoe in a dryer. That is the daily life of many small, icy bodies. Steady is a bedtime story lumpy ice rock almost never tells. Their shapes are awkward, their insides are patchworks of dust and frozen gas, and their spins respond to every nudge like a weather vane in a gusty alley. The fun part is that those wobbles are not random noise. Hidden in the chaos is a choreography you can read if you know which beats to listen for. Start with the idea of principal axes. Any solid object has 3 special directions tied to how its mass is distributed. If you spin the object exactly around one of those directions, the motion is tidy. Real comets and interstellar visitors make a promise to tidy motion and then forget it immediately. A slight push off that special direction, or an uneven mass inside, and the object begins to tumble in what physicists call non-principal axis rotation. In plain words, the body spins, but the spin axis itself wobbles and traces a slow cone in space. It is the celestial equivalent of balancing a broom on your hand while someone keeps poking the handle. Internal structure matters. Many small bodies are not single stones. They are rubble piles held together by gravity and a bit of ice acting like glue. When such a stack spins, grains shift, voids settle, and tiny landslides redistribute weight. That moving furniture changes the natural spin preferences, which changes the wobble, which changes how sunlight hits each patch, which changes the jets, which changes the torques. Welcome to the feedback loop. Population, everyone. Earth is basically a rock that won the cosmic lottery. These travelers are the lotto tickets crumpled in a pocket with a secret map. Now bring jets into the picture. We already met them as accidental thrusters, but their relationship with spin is where the real drama lives. Imagine a single vent on the morning side that wakes up after local sunrise. It puffs harder when that patch faces the sun and relaxes as it rotates into evening. Every putter and pause applies a little twist. If the vent sits away from the exact center, the twist is off balance and adds a torque that either speeds up or slows down the spin. Multiply this by a handful of vents with their own schedules, and you get a drum circle of torques that can change not only how fast the body spins, but also which way the spin axis points. Tilt the spin axis, and the seasons on the surface shift. A vent that snoozed for weeks can suddenly bask in sunlight, turning on like a geyser. That new roar alters the torque budget again. Over days, the object can drift from a neat, near-principal spin into a full tumble. Over weeks, it can drift back if the active areas migrate or fade. The phrase time-dependent does not do this justice. It is more like mood-dependent, with the mood set by a patchy crust and a star that does not care about your schedule. Sunlight itself can twist a body even without gas. When one face is brighter or rougher, it absorbs and re-radiates energy differently than its neighbors. That uneven thermal glow produces a tiny net torque, a slow whisper that says, "Turn this way." For a very small, dark object, this whisper can accumulate into a noticeable change in spin over months. It is patient work, like a river carving a curve in a bank. But the river never sleeps, and the bank is not as solid as it looks. How do we know any of this is happening? If we cannot stroll up and give the nucleus a nudge, we listen to the light. As a lumpy body turns, its brightness rises and falls in a repeating rhythm. That rhythm is a light curve, and it is one of the cleanest telltales of spin. A single hump, repeating like clockwork, points to simple rotation. A light curve that meanders, doubles up, or shifts its pattern over a few nights hints at tumbling. Sometimes you can even catch the slow wobble period, separate from the fast spin period, like hearing the beat of a drum and the sway of the drummer's shoulders at the same time. There are other clues. Narrow jets that look straight in one image can kink or pivot in another if the source region has rolled to a new angle. Dust fans can sweep like lighthouse beams across the tail, leaving curved striations that encode the schedule of rotation. A sudden change in the period over a week suggests that a cliff collapsed or a vent opened wider, changing the torque mid-season. Each of these is a line in the diary the comet writes with sunlight and vapor. Tumbling is not free. It costs energy, and the small internal friction in a rubble pile acts like a brake on complicated motion. Over long stretches, that friction can damp the wobble and coax the spin back toward a principal axis. But the same jets that push the wobble toward order can also restart the chaos. The result is a tug of war between damping and driving. Some bodies settle down, others live on the edge, never quite tidy, never fully wild, like a campfire that keeps finding new pockets of wood to flare. Why should we care about such fussy details? Because spin controls what the sun can do to the surface, and what the surface does to the path. A slowly rotating object with most of its activity in one hemisphere will feel a preferred shove in a particular direction, which translates into a small, persistent drift in the trajectory. A rapidly tumbling object smears that shove around, producing a gentler net effect, but a more complicated light show. Spin also governs breakup risk. If the period shortens toward a dangerous threshold, a weak, two-lobed shape can pull itself apart. Tumbling can either slow that march or, in unlucky geometries, hasten it. In short, spin is the hidden metronome of a traveler's life. It sets the cadence of jets, it angles the sunlight, and it decides whether the next act is a steady hum or a cymbal crash. Steady is a fantasy because the stage keeps tilting, the actors keep changing costumes, and the spotlight keeps moving. Up next, we follow the cymbal crash. What happens when stress finally wins, when a surface slumps or a fragment peels away, and how even a crumb can rewrite the story the orbit fit tries to tell. Chapter 9. Breaking news. Literally, fragmentation scenarios. Comets are not carved statues. They are pastries that flake. When a brittle surface heats, cools, flexes, and breathes gas long enough, something eventually gives. A ledge loosens, a seam opens, or a buried pocket of pressure finds a shortcut to daylight. If a crumb falls off your croissant, you still have breakfast. The orbit fit, however, gets crumbs in the keyboard. Fragmentation is messy in the prettiest way possible. The sky brightens, the shape of the coma changes, and the center of mass quietly relocates, while the center of brightness performs a drum solo. Let us start with the gentlest failure mode, surface spallation. Think of a sunlit crust that expands during the day and tightens at night. Repeated cycles fatigue the outer millimeters until thin plates snap off. Each plate is large enough to scatter sunlight well, yet light enough to be bullied by radiation pressure. The immediate result is a cosmetic glow-up. The coma looks fluffier, the tail grows a little broader, and observers record a surge in brightness that fades over days as the flakes disperse. Dynamically, the nucleus is nearly the same mass as before, but the measured position can shift slightly because telescopes, especially in shorter exposures, are attracted to the brightest clump, not the true core hiding inside its own glitter. A notch more dramatic is a cliff collapse. Imagine an overhang eroded from beneath by gas escaping through porous layers. One moment it is a proud balcony, the next it becomes an avalanche of blocks and powder. The instant those blocks lift off, gas outrushing through the fresh wound gets an unclogged exit, and the local activity jumps. Two things happen to your trajectory story. First, the thrust pattern changes because the vent geometry changed. Second, the mass distribution changed because part of the comet is now sunlight-friendly rubble. The nucleus may experience a small recoil as the avalanche accelerates outward, like a person stepping back when they drop a heavy box. It is subtle, but over days, such a recoil can lean the computed path just enough to make last week's best fit look suddenly optimistic. Then there are true splits, when a stress line propagates through the interior and the nucleus separates into two or more coherent chunks. This is rare, but when it happens, the sky writes it in capital letters. Brightness can spike dramatically. Two cores emerge inside the coma, and in good seeing, you can watch them drift apart along a line that telegraphs the original spin and the internal fault. In calculations, this is a soap opera. Which core are you measuring on night 1 versus night 3? Does the faintest secondary become briefly brighter because sunlight hits a fresh face at a flattering angle? If you fit a single body through those measurements, the residuals will plead for mercy. Fragmentation signatures have favorite fingerprints. One is the formation of synchrones and syndines, those graceful strands of dust that peel off in sheets grouped by release time and grain size. Another is forward scattering, a lighting geometry in which dust ahead of the sun observer line glows like confetti catching a spotlight. That effect can make an outburst look even more intense from certain angles, tempting you to attribute the brightness jump to a power surge at the source rather than to a stage light trick on the debris. The moral: when a comet sheds, both physics and theater show up. Thermal and mechanical triggers team up to start these events. A rapidly changing spin can pull on a weak waist until it yields, especially in a two-lobed body where the neck is already stressed. A sealed cavity under a crust can build pressure until a zipper opens along an ancient crack. Even tidal stretching during a not-too-distant solar pass can prime the fault lines so that a quieter push later, perhaps a routine sunrise, sets them free. None of this demands exotic material or hidden engines. It demands time, heat, and a structure that was never as uniform as it looked in the first place. From the observer's seat, the chaos condenses into a handful of practical headaches and delights. The measured centroid of light walks around unpredictably as new dust fans light up one side more than the other. Automated pipelines that assume a point-like core can be lured toward the brightest plume. Photometric curves develop shoulders and plateaus, where once they had tidy peaks, colors can shift as fresh, reflective dust briefly dominates before dark space grit takes over again. If you watch with a high frame rate camera, you might even witness jet directions change within a night, as newly exposed vents inhale sunlight and start shouting. Modelers cope by switching from single-body dynamics to multi-component fits. You treat the brightest core as the primary and the runner-up as a secondary with its own micro-trajectory, both moving in the shared gravity field while feeling their own tiny non-gravitational nudges. It is computationally fussy, but conceptually clean. 2 pastries, 1 plate, many crumbs. When done well, such fits can back out the moment of separation, estimate the mass ratio of the fragments, and predict whether the secondary is durable or doomed to become dust in a few rotations. One charming byproduct of fragmentation is a brief cometary meteorology. The coma grows structure, arcs, striae, and shadows, where denser dust curtains block sunlight. As the fragments separate, their individual comae can overlap, creating interference patterns any photographer would envy. In deep images, you may spot a faint, narrow trail hugging the path of the nucleus. That is the graveyard of the heaviest pieces, too stubborn for light to push and too slow to wander far. Follow that trail long enough, and you read the object's shedding history as clearly as footprints across snow. Why do we care beyond the spectacle? Because fragmentation is a reset button for every assumption you made before the event. Activity maps change, talk budgets change, and predictions computed from last week's quiet data turn suspicious. For an interstellar traveler, the stakes are higher. You have a short audience, and each shedding episode edits the script. If you want the right ending, you must rewrite the middle as soon as the pages fall out. All of which brings us to a humbling truth. Not every kink in a plotted path is the cosmos whispering secrets. Some are crumbs in the keyboard, courtesy of a visitor that decided to exfoliate at the worst possible time. Next, we will zoom out from the breaking nucleus to the systems that try to measure it, and sometimes get fooled, exploring how calibrations, catalogs, and code can conjure mischief even when the sky behaves perfectly. Chapter 10: The Instrument Trap. When data pipelines prank you, there is a special kind of plot twist where the villain is not the comet, not gravity, not sunlight, but the spreadsheet. The first rule of astronomy: trust, but verify. Then verify the verification. Telescopes are honest. Data pipelines are honest too, but they can be hilariously literal. Ask a question slightly the wrong way, and they will gift you a beautifully wrong answer, wrapped in statistical confidence. The cosmos is calm. Your software is the raccoon in the pantry. Let us start with flat fields, the foundation of clean pixels. A camera's detector is not a perfectly even meadow. Some patches respond a little stronger, others a little weaker. To tame that, astronomers take images of a smooth light source, then divide the science frames by this calibration to level the field. It is kitchen counter wisdom: wipe before you plate. But if your flat is imperfect, or if dust motes wandered across the optical path between calibration and observation, you can imprint gentle dimples and highlights that persuade the centroid algorithm to pick a slightly shifted sweet spot. The comet did not move, your hill of sensitivity did. Dark frames add a second flavor of mischief. Detectors have their own thermal sparkle, even in complete darkness, and the rate changes with temperature and time. You subtract a dark frame to remove that glow. Use a dark that is too old, or at the wrong temperature, and you leave a faint residue or carve a shallow divot right where your target sits. Now imagine stacking a dozen such frames. The residue becomes a ghost that tugs the measured position like a shy child tugging a sleeve. Then there is the star catalogue, the sky's address book, modern astrometry maps, your image to a catalogue of known star positions, true to a level that would make a cartographer blush. But catalogues evolve. New releases correct old biases and improve proper motions. If your pipeline switches catalogues mid-campaign without a clean handoff, the celestial grid can tilt by a whisper. That whisper is enough to put a dot, a hair's width off, and a hair's width off across several nights can masquerade as a gentle swerve. It is not that the stars moved. Your ruler changed font between pages. Saturation is the diva in this play. Bright stars in the field can flood pixels, bleeding charge into neighbors and recentering the local brightness profile. If your tiny target passes near that sparkle, centroiding software may be lured away from truth by the glitter. Even worse, a saturated core can trick background estimation into thinking the sky is brighter than it is, leading to overzealous subtraction that nibbles at your comet's faint edges. A trimmed halo looks off-center, and the fit obediently follows the new, wrong center. Space is fine. Your camera needs a snack and maybe a nap. Speaking of background estimation, the sky is rarely flat. Airglow, scattered light from the moon, and instrument reflections paint gentle gradients. Many pipelines remove those with a smooth model. Smooth is great until your model decides the coma is part of the gradient and peels it away. The remaining core appears sharper and possibly offset because you surgically removed the faint shoulder on one side. A tidy profile is satisfying, but sometimes tidy equals tattletale. Point spread functions, the shapes stars take on your detector, are another subtle pitfall. We often assume a simple bell curve. Real optics deliver a bell curve with swagger, asymmetry from slight focus errors, wings from scattering, and tails that lengthen toward the edges of the frame. If your object sits near a corner while your model assumes the center, the centroid will slide a little toward whatever direction the wings prefer. When you later align and stack images that rotate relative to the sky, these winged shapes swirl, quietly remapping where the brightest pixel lands. Tracking choices can act like a mischievous editor. If your mount locks onto the comet's predicted motion, stars smear into trails. Some software then fits and removes those trails to keep the background neat. Depending on the algorithm, it might subtract more on one side of the comet than the other, shaving brightness asymmetrically. If instead you track the stars, the comet streaks, and de-streaking later requires resampling that softens one axis more than the other, the net effect is a center of light that marches a tiny step sideways. Not dramatic, just enough for a false whisper in the residuals. Timestamps are the plot device no one expects to matter until the third act. A misset clock by even a small fraction of a minute can shift a predicted position by just enough to raise eyebrows. Network outages, daylight-saving hiccups, or a sneaky laptop that reverted to a time zone from last week's conference can plant an error that looks physical but is pure bureaucracy. The object did not turn. Your calendar did. Compression and debayering also deserve a side eye. If you save images with heavy compression to speed downloads, faint gradients can break into blocky steps that fool background models. If your color camera converts raw mosaics into full-color frames on the fly, the interpolation kernel can slightly displace the apparent center of a small, soft object relative to the underlying pixel grid. These are tiny effects, but tiny is the favorite flavor of orbit fits. Software defaults, the silent influences, tie all of this together. Aperture sizes, centroid methods, outlier rejection thresholds, and the choice to weight points by reported uncertainty or treat them equally. All of these are decisions, even when you do not touch a slider. Change one default midstream, and you might as well have switched lenses without telling your notes. The pipeline is not capricious. It is obedient. It does exactly what you told it, even if you did not realize you were telling it something new. So how do you keep the pipeline from pranking you? You pair every automated run with sanity checks. You measure a couple of bright, unsaturated stars and make sure their recovered positions are as good as the catalog you used. You process a night 2 different ways and confirm the orbit fit does not depend on a single magic setting. You re-reduce a subset with an older catalog to see if the alleged nudge survives. You share raw frames so other teams can try their own recipes. You let humility be your co-author. Here is the payoff. When you clear these hurdles and the gentle deviation still stands, your confidence blossoms. Not because the anomaly is big, but because the gauntlet was brutal and it survived. Only then is it worth asking what nature is whispering. Is it events rhythm, a seasonal twist, or something stranger? That is the joy of a clean pipeline. You hear the sky, not the kitchen. Next up, we will lift our eyes from the control room to the red planet's balcony and ask what orbiters around Mars could see that Earth cannot. Front row seats for a traveler who is in a hurry. Chapter 11, Mars has front row seats. What orbiters could see. If Earth is the noisy ground floor of the space apartment building, Mars is the quiet balcony with a perfect sightline. When an interstellar traveler sweeps by, the red planet can offer angles and lighting that Earth just cannot buy, no matter how many telescopes we wheel onto mountaintops. Think of it as the universe's best balcony tickets, complete with crisp air, fewer clouds, and a stage light that hits the comet from a different side. From that perch, Mars-based and Mars-orbiting instruments can catch details that turn a fuzzy mystery into a readable diary. Start with geometry, the secret sauce. A visitor's coma and tail are 3-dimensional sculptures. From Earth, we might view that sculpture face-on, with dust and gas flattened into a bright pancake. From Mars, the same structure could be seen edge-on, revealing layers, shells, and rays that were invisible before. That shift alone can tell us whether a jet is a narrow needle or a broad fan, and whether the dust is released in pulses or as a steady sigh. When 2 observers watch from far apart, you can triangulate the direction of a jet, the same way you triangulate a thunderclap by timing it from 2 towns. The result is not just a prettier picture. It is a map of where thrust is being applied, which matters for understanding subtle nudges in the trajectory. Consider high-resolution imaging from a Mars orbiter. A camera designed to spy on boulders and landslides can repurpose itself as a comet portrait artist. Short, rapid exposures freeze the inner coma, letting us isolate the tiny bright core from the glow around it. Once the core is pinned down, you can watch how the center of brightness drifts as dust fans grow and fade. That drift, measured night by night, is a clue to where vents are waking up on the rotating surface. The kind of detail that is mush from Earth's atmosphere can turn crisp in the dry, steady air above Mars. Color and spectroscopic eyes sharpen the picture. Instruments that split light into colors can sniff for telltale emissions from common gases and from exotic fragments liberated by sunlight. The exact blend says something about which ices are present and which layers are being excavated by heat. Even better, the strength of those signals across the coma tells you where fresh material is being released. A linear brightening that points at a specific sector of the nucleus, that is a fingerprint for a source region. A crescent that lights up only when the sun falls at a low angle, that hints at cliffs or pits acting as vents. Mars is not just a second camera, it is a lab bench in orbit. Mars brings a gift that Earth struggles to provide: clean occultations. If the visitor's path takes it near the limb of the planet, as seen from orbit, a spectrometer can watch starlight or sunlight skim through the coma right beside the planet's edge. The planet acts like a ruler in the frame, locking the geometry. As the cometary gas drifts across the line, absorption features rise and fall like a heartbeat, revealing density and composition without the blur of a full-face view. Do the same trick again a day later from a slightly different orbit, and you can watch how the coma grows or relaxes, which feeds directly into models of vent strength and rotation. Plasma instruments around Mars add another dimension. The ion tail of a comet is a conversation with the solar wind, and Mars has microphones all over that room. By measuring charged particles and magnetic fields upstream and downstream of the planet, orbiters can detect when a comet tail brushes past. A sudden change in field direction, a surge of pickup ions that match the visitor's chemistry, a ripple that moves with the wind like a flag snap. Each is a timestamp that locates the tail in three-dimensional space. Combine that with images, and you can sketch not just the coma's shape, but the spine of the ion tail, along with any kinks or disconnects triggered by space weather. The solar wind forgot its umbrella. Mars brought a sensor. Rotation clues multiply from the balcony view. A nucleus that tumbles will send jets sweeping across space like lighthouse beams. From Earth, those beams might blur into a wash. From Mars, with a different phase angle, the same beams can cut distinct paths across the inner coma. By stacking images in the visitor's frame of motion, you can trace repeating arcs and measure the beat between them. That beat is a rotation period. If the beat drifts over a week, you can catch the torque from changing vents in the act. It is like watching shadows slide across a sundial from two courtyards at once. Even simple photometry, the art of measuring total light, gets a power-up. With Mars on the far side of the visitor relative to Earth, one observer might view the dust at a forward scattering angle. Think of dust glowing like glitter near sunset, while the other sees it under a harsher side light. Differences between the two brightness curves let you separate how much of the glow is dust geometry versus real changes in output. That untangles the age-old question: did the comet actually get busier, or did the lighting simply flatter yesterday's hair? Mars surface assets can join the show too. A rover's navigation camera or a lander's sky monitor can contribute time-stamped, wide-field images of the tail and of bright outbursts. These are not glamour shots, but they add cadence. When orbiters slip behind the planet during parts of their loop, surface watchers keep the heartbeat going. That continuity matters for turning scattered episodes into a narrative of when jets switched on, how long they stayed loud, and whether the object's day and night sides behave like different characters. Because Mars is a separate platform, it also buys parallax for free. Small disagreements between where Earth and Mars place the nucleus on the starry wallpaper are not errors. They are a three-dimensional gift. Fold those positions into an orbit solution, and the uncertainty shrinks. That tighter solution makes it easier to isolate any non-gravitational push from jets. Because gravity's part of the story is no longer fuzzy. The net effect is a cleaner separation between physics and illusion. Finally, Mars operates on Mars time. That means instruments catch the traveler at hours when Earth-based telescopes may be clouded out, sunlit, or busy with other targets. The red planet's balcony does not replace Earth's orchestra pit. It adds percussion and a spotlight that swings from another direction. Together, they turn a whisper of clues into a tune you can hum. So yes, Mars has front row seats, and the view is not just pretty. It is diagnostic. From jet directions and rotation beats to ion tail kinks and coma chemistry, a Martian vantage locks in the truth Earth alone would half see and half guess. Next, we will peer into the visitor's recipe itself, what the colors, glow, and faint breaths of gas reveal about the ingredients, and how composition sets the strength of those tiny thrusters that keep rewriting the script. Chapter 12. What it is made of. Spectra, colors, and clues. If you want to know what an interstellar traveler is made of, you do not crack it open with a chisel. You listen to its light. Every grain of dust and every puff of gas turns the visitor into a faint orchestra. And spectroscopy is the seat where you can separate the flutes from the drums. When sunlight bounces off a dusty crust or slips through a cloud of vapor, it leaves tiny fingerprints that tell you which ingredients are on stage. If it looks like a comet and breathes like a comet, the burden of proof is on Mystery Probe. Let us start with the dust, because dust writes the headline you can actually see. A bare rock reflects light in a simple way. A dusty, porous surface gives the reflected spectrum a gentle reddish tilt. The colorist's way of saying there are complex carbon-rich grains here. That tilt is not a single hue. It changes with viewing angle and with the size of grains hanging in the coma. Fine, fluffy grains scatter blue light differently than red, so a sudden dust release can make the whole object look subtly warmer or cooler in color over a night. When observers measure brightness through different filters and compare the ratios, they are not judging its fashion sense. They are mapping grain sizes and coatings. Ice speaks in the near-infrared, where it shows broad, rounded dips in reflectance. Water ice is the loudest vocalist, but other ices join the chorus. Carbon monoxide ice, methane, and friends that come from the deep freeze. If those dips are shallow, you are seeing ice that is crusted over with dust. If they deepen after an outburst, it hints that fresh, cleaner ice has been exposed. The shape of the dips matters too. Rounded, smoothed features suggest intimate mixing of ice and dust at very small scales, like cocoa powder folded into whipped cream. Sharper features suggest cleaner patches, more like ice chips, scattered onto dark soil. Gas glows by emission, which is the universe's version of neon signs. Sunlight breaks molecules apart and shakes them up. As they settle down, they radiate at specific colors. Hydroxyl tells on water ice because it is what you get when sunlight teases water apart. Diatomic carbon glows in a way that makes the head of a comet look green in some images. Cyanogen has its own bright lines. None of these are science fair curios. They are the basic exhale of a fresh, sunlit coma. If those lines strengthen when a particular patch rotates into view, you have found a vent with personality, and likely a chemistry set that is richer there than elsewhere. Color gradients across the coma add a second layer of clues. Close to the nucleus, grains are fresh, jagged, and sometimes coated with frost. As they drift out, sunlight bakes them, darkens their skins, and strips fragile coatings. If you map color from the core outward, you can watch that makeover in real time. Slightly bluer near the source, redder farther out. as carbon-rich crusts develop, that gradient is a clock. It tells you how fast grains leave the neighborhood and how quickly sunlight edits their surfaces. Polarization, the way light waves line up after bouncing off particles, sounds abstract, but it is a direct probe of texture. Light, scattered by smooth, glassy grains, behaves differently than light bounced from fluffy, fractal clumps. By measuring how the alignment changes with phase angle, observers can distinguish a powder of fused snowflakes from a spray of compact pebbles. That, in turn, feeds into how sunlight pushes the dust and how easily gas can drag it, which loops back to how strong the jets can become for a given composition. Why does composition matter for jet strength? Because not all ices wake at the same temperature. Water ice waits for a closer embrace from the sun before it sings. Carbon monoxide and other deep freeze ices can sublimate in the far outskirts, turning on the thrusters while the visitor is still shy and faint. A nucleus rich in the early birds will spray a thin, steady breath long before the bright season, shaping a coma that is wide but subtle. A nucleus dominated by water ice will nap until the inner system, then ramp up dramatically, switching from whisper to shout as morning sunlight drills into warmable layers. The layered mix matters too. If dusty crust caps a pocket of easy-to-lift ice, the first hairline crack can turn a simmer into a geyser, and the spectrum will flip from dust-dominated to gas-rich almost overnight. Sometimes spectra catch a seasoning of complex organics, broad features that hint at tarry, ancient chemistry laid down in the nursery where the object formed. Those materials are excellent at soaking up light and converting it to heat, which deepens surface warming and encourages localized venting. They also darken the overall look, which means the object must be larger to reflect the same amount of sunlight as a clean, bright snowball. Now brightness curves and spectra link arms. If the object is dim for its distance, yet shows strong gas lines, you are likely dealing with a big, soot-coated engine hiding under a matte finish. There is a twist that keeps the detective work honest. The center of brightness is not the center of mass. If a cloud of fine, highly reflective grains blooms off one flank, the image centroid can slide toward the glitter, even though the nucleus sits a little to the side. Spectroscopy helps you resist that mirage. The sharpest gas lines usually peak near the true source, not the brightest dust plume. By mapping gas and dust separately, you can anchor the nucleus and treat the sparkle as decoration rather than driver. All of these clues build a profile that you can test against ideas. A natural traveler will show a chemical family tree with lines and bands in ratios that make sense for mixed ices and processed dust. The glow will vary with sunlight in ways that track rotation, local time, and season on the surface. If instead you were staring at an engineered reflector or a powered vehicle, you would expect oddities. A reflectance curve too smooth and too flat for dusty ice, emissions that do not match known molecular families, or brightness changes that line up with geometry, favorable for control rather than with local morning and afternoon on a turning body. The bar is high, and it should be. Mystery probes do not get a free pass when ordinary ice and dust can sing exactly the tune we hear. In short, light is a truth serum. It tells you what the visitor is made of, how those ingredients are layered, and which parts of the surface are doing the heavy lifting. With that recipe in hand, you can predict how strong the jets should be and how the coma should evolve, then see if the sky agrees. Next time, we will loosen the tie and step into the speculative lounge. Imagine an interstellar craft surfing starlight or whispering with magnetic fields. What would we look for, and how would we know we were not fooling ourselves? Chapter 13, The What If Hour, Alien Tech Thought Experiments. Let us step into the speculative lounge where the lights are low, the curiosity is high, and the bouncer is evidence. We are not declaring anything extraordinary. We are trying on possibilities the way you try on jackets you probably cannot afford, just to feel the fabric. Black holes are the universe's way of saying delete browsing history permanently. Smart probes would be the universe's way of saying we read it first. If an interstellar visitor behaved in a way that ordinary ice and dust could not explain, what engineered tricks might be on the table, and what footprints would they leave in our data? Start with a light sail, because sunlight is the only fuel station that never closes. A sail is a broad, very thin surface that trades mass for area, letting photons nudge it with a steady hand. Unlike a fluffy dust coma, a well-built sail keeps a consistent attitude on purpose. Its brightness would not wander randomly with rotation, the way lumpy rock does. Instead, you would see sharp, geometry-driven glints when the sun, the sail, and the observer line up just right. The color of the reflected light could be unusually flat, the way polished films reflect across many wavelengths. If the sail tacked, you would not get bursts timed to local noon on a turning nucleus. You would get changes timed to favorable push angles, like a windsurfer carving across a steady breeze. A light sail does not make a tail of gas. It makes a signature of control. Magnetic sails live in the invisible realm, but their effects would not be shy. The solar wind is a river of charged particles. A magnetic field looped from a craft can push against that river the way a parachute pushes against air. A device like that would not care much about sunlight. It would care about the strength and direction of the solar wind and the local magnetic field. If a traveler accelerated or shifted direction following a space weather event, and if that shift happened without any dust or gas cue, a magnetic sail would step onto the suspect list. A big field would also sculpt the ion environment nearby, creating a miniature cavity that plasma instruments on a passing spacecraft could feel. It would be the only time a bubble bath with no soap made sense. Then there is active steering, the old-fashioned way, thrusters. Chemical thrusters spit exhaust that glows in familiar lines. Electric thrusters whisper with ionized propellant. Either way, you search for spectral residues that do not belong to natural cormay, and for heat patterns that do not match sun-warmed rock. A craft that rotates to align a nozzle would create regular, controlled pulses, not the moody, season-dependent fits of a vent buried under dust. The accelerations would be short, crisp, and repeatable at intervals tuned to navigation, not to dawn and dusk on a tumbling surface. If the thrust schedule lined up with the needs of a planned encounter or a gravity assist, you would have a plot twist worth clearing your schedule for. What about a beacon ping? The shy hello? A reasonable probe may keep quiet until it has a reason to speak, and we are not always the reason. But if it did speak, the clues would live in narrowband radio or in optical flashes that repeat with machine neatness. Nature loves spectra with broad shoulders and fuzzy edges. Engineers love tidy lines. A beacon would not just be narrow, it would be coherent and possibly polarized in a precise, unambiguous way. If the signal pattern counted primes or traced a simple map, well, you would hear 1,000 keyboards light up at the same time. Of course, camouflage is also a possibility in this daydream lab. A smart probe could wear a jacket of dust deliberately, looking like a comet while hiding a frame inside. But even a sneaky disguise leaks tells. A coated frame would keep inertial stability better than a rubble pile. Light curves would be smoother than they deserve to be for an object with that much apparent texture, and the dust would not age the way natural grains do. Fresh coatings look different from baked leftovers, and unless the probe is running a full-time cosmetics counter, the pattern would slip. One elegant idea is a blended concept, a sail that can shift from sunlight push to magnetic push, making use of whatever the star gives on a given day. That would look like a traveler switching tires mid-race. You would watch for accelerations that track either the photon flux or the solar wind state, with quick changes between modes that are too nimble for geology. Nature can do nimble with outbursts, yes, but outbursts drag dust and gas along as confetti. A blended craft would leave control without confetti. Now, what would genuine alien navigation look like over weeks? It would respect efficiency. The path would not zigzag for drama. It would curve in ways that conserve momentum and exploit free energy like sunlight or wind. It would treat planets as free catapults, timing passes to shave or add speed. It would not waste days fighting the tide of gravity if a slightly different aim long in advance saved orders of magnitude of effort. Engineers love lazy elegance, and so does the cosmos. The trick is that nature already draws elegant curves. The difference would be intent measured through timing, repetition, and the refusal to correlate with any natural day-night cycle on a rotating body. The human part of this thought experiment is the most important. We are pattern hunters with caffeine in our veins. We can see a face in toast and a strategy in static. So the rule here is discipline disguised as romance. Demand multiple independent signals. If a putative sail glints, confirm with polarization and phase angle tests. If a magnetic maneuver coincides with a solar wind shift, check for gas lines and thermal glows to make sure it is not a natural outburst hitching a ride on the weather. If a beacon teases a tone, put 3 dishes on it and watch the sky around it for reflections, satellites, and the usual suspects of human clutter. This hour is for wonder, not for verdicts. The marvel is that our instruments are now good enough to even ask these questions honestly. We are moving from myths to diagnostics, from stories to tests. If the universe wants to sneak a clever postcard through our mailbox, we finally have a way to check the watermark. Next time, we will turn that instinct for rigor into a checklist. The signatures that would actually move a claim from playful speculation to evidence that can survive a peer review storm. Chapter 14. If it were a probe, what evidence would convince us? Let us trade campfire stories for a checklist. If an interstellar visitor were actually a machine, what signatures would be sturdy enough to move us from eyebrow raise to bring a chair? This is serious. The rule is simple. Extraordinary claims need evidence that is testable, repeatable, and allergic to hand-waving. We are not trying to smuggle science fiction past security. We are asking what would survive in the bright light of many telescopes and many skeptical minds. Start with the glow that does not glow like nature. Natural coma radiate, because sunlight shakes molecules in dust, which then relax in familiar ways. A machine could produce non-thermal emissions that refuse to match that cookbook. Think narrow lines in odd places, or microwave and radio features that stay razor-thin while the rest of the spectrum sloshes around with rotation. If a tone holds a steady pitch while the object spins, you are not hearing a vent, you are hearing an oscillator. Engineers love neat frequencies, the way cats love sunny windowsills. Next, coherence and structure in radio. A beacon would not be a messy hum. It would be a clean note with deliberate modulation. Imagine a signal that repeats a pattern too tidy for geology, equal length pulses, prime number spacing, or a drift that perfectly matches a calculated approach to a planet for a gravity assist. Ask 3 antennas on different continents to watch at once, that they all record the same choreography, and the pattern follows the object across the sky. You have something that transcends local interference or an overachieving satellite in Earth orbit. Now the light curve. Natural bodies flicker as they turn because they are lumpy and patchy. The timing may wander as jets ramp up or die back. A controlled surface would play by a different beat. You would see specular flashes that align with exact phase angles, as if a polished panel were choosing when to wink. Those flashes would repeat on schedules set by desired geometry, not by morning and afternoon on a spinning crust. If the winks adjust to keep the push from sunlight optimal, brighter when the sail needs a shove, dimmer when it does not, you are watching intent wear a mirror. Thermal behavior can betray a frame beneath the fluff. Rock and dust heat slowly and cool slowly, and they do it in a way that depends on texture. A thin engineered foil can spike hot when the sun hits and then shed heat in a hurry when it turns away. Infrared measurements, taken over a few rotations, would plot those spikes like a heartbeat. If the peaks align not with local noon, but with a scheduled maneuver window, that is not weather. That is a plan. Course corrections are the big-ticket item. Nature can push, but it pushes according to sunlight, spin, and vent location. A probe would change direction when geometry says the return on momentum is best, even if that moment lands at a weird local hour. Map the ephemeris residuals, the little differences between where gravity says the object should be and where it is. Over weeks, if you see repeated crisp nudges that arrive at intervals matching optimal sail tacks or magnetic push directions relative to the solar wind, and those nudges refuse to line up with any reasonable rotation or seasonal model, you are looking at steering, not weather. Gravity is the friend who never texts back. Deliberate maneuvers are the friend who texts on my way and shows up to the minute. Material that will not behave like comet dust is another strong clue. Scoop the spectrum of the dust plume and compare it with the usual suspects. If the grains reflect like multi-layer films, with a flat, tailored color response that shrugs at ultraviolet tantrums, that hints at coatings rather than tarry organics. Polarization is a telltale too. Fluffy natural grains, polarized light in a particular curve with viewing angle, laminated sheets or woven meshes would produce a different curve, crisp and repeatable. Nature loves variety. Factories love standardization. Radar can help. Send a ping and listen for the echo. A rubble pile scatters. A flat plate can ring like a dinner bell, returning a bright, specular glint at just the right angle. Watch that glint move as the object turns. If the timing says the surface is larger and smoother than any reasonable cliff, and the echo repeats with machine regularity, you can start sharpening your pencils. Plasma signatures matter for sails that play with the solar wind. A magnetic sail would carve a pocket in the charged particle flow that is too tidy and too symmetric for a transient ion cloud. If spacecraft along the wind line record a cavity with edges that stay razor clean while the visitor changes its attitude, that looks like a field generator, not a one-time outburst. Bonus points if the cavity size scales with the wind in a way that screams control rather than accident. One of the most persuasive lines of evidence would be choreography with planets. An efficient craft treats gravity wells like stepping stones. If you catch a traveler shaving speed just before a planned flyby, then adding speed afterward with small course trims placed where they buy the most return, that is a flight plan. Nature can wander into one neat assist. A sequence of assists that echo a minimal fuel path is less a coincidence and more a signature. Then there is the long shot, an intentional reply. If targeted signals are beamed and the visitor answers with a delayed echo that carries content, game over. But we do not have to be that lucky to be convinced. A mosaic of independent anomalies can stack into a wall. Narrowband radio that marches with the object, optical flashes at geometrically meaningful angles, thermal spikes that ignore local noon, course nudges that arrive on optimal schedules, and dust that behaves like engineered films. Each piece by itself is interesting. Together, they spell a word we dare not use lightly. Through all this, the tone remains skeptical, with a smile. Earth is basically a rock that won the cosmic lottery. The prize does not include skipping steps on evidence. We require multiple instruments, multiple teams, and blind tests. We test hypotheses that could make the signals vanish if our assumption is wrong. If the signals refuse to vanish and instead sharpen under scrutiny, then we pour coffee and write carefully. Because if it were a probe, we would want to be right for the right reasons. Next time, we pivot from romance back to responsibility. How the people who guard our skies assess risk, how no threat is calculated, and what a calm, grown-up response looks like when the cosmos throws a curveball. Chapter 15, Planetary Defense Mode. Risk, rigor, and reality. When a new object shows up on the cosmic attendance sheet, The first people to stop sipping coffee are the planetary defense teams. Space agencies are basically hall monitors for the solar system. They do not chase drama, they chase probabilities. Their job is to look at a faint dot, imagine 10,000 futures for it, and then stop any future that includes our blue hallway getting a surprise locker check from above. Let us decode how hazard gets scored without turning this into a fire drill. First, position dots are collected by survey telescopes that scan big slices of sky each night. Those dots are converted into a first draft path and shipped to a clearinghouse that posts the discovery. Within hours, follow-up observatories join the relay, adding more dots so the path tightens. Think of it like tracing a curve with a handful of thumbtacks and then pushing in a dozen more until the string between them quits wobbling. Only after that tightening begins does anyone even whisper about risk. Hazard does not mean it looks scary. Hazard is a number born from possible paths. To get that number, software takes the best-known position and velocity and then dials the uncertainties a little to the left and right, forward and back, like tuning a radio through static. Each tiny change spawns a possible future track. If a sliver of those tracks intersects Earth on a given date, the object earns a Nungor impact probability for that date. It is not a prediction. It is a branch on a decision tree that says, if the world is exactly like this and not like that, here is where the pebble meets the pond. Two scales help translate those branches into human language. One is a color-coded ladder that runs from harmless gray to attention-grabbing red. The other compares the event's odds and potential energy to the background rate of similar strikes. The first tells you whether an object deserves a headline or a nap. The second tells the professionals whether they should nudge schedules, pull in more telescopes, or simply let the normal cadence gather what is needed. The important thing is that both scales are designed to move down as rapidly as they move up. Most newcomers briefly flirt with concern and then settle to benign once the dots accumulate. That is not a conspiracy. That is how uncertainty behaves when you shine more light on it. Now, about that word close. Headlines love it. Scientists define it. In space, close can mean passing within a few distances between Earth and Moon. That is astronomically near and domestically very far. You could stack many Earths inside that gap and still have room for snacks. An object that passes within even a few 100,000 kilometers is an exciting photo opportunity and an utterly boring safety story. Close is geometry, not danger. If you hear no threat, it does not mean panic quietly. It means exactly what it says. The family dog barked at the mail carrier, and the mail carrier already walked on by. Why are agencies so confident saying no threat? Because the math is married to verification. Every time a fresh measurement comes in, the path gets recomputed and the future branches are pruned. The small slice of futures that once grazed Earth either disappears or becomes a razor-thin thread that still needs more data before anyone raises a hand. It is like watching a storm forecast cone tighten and slide away from your town as new radar frames arrive. Meteorologists are not hiding the rain. The storm is simply aiming elsewhere. Communication is part of the job. When teams publish risk lists and daily updates, they are not stoking fear. They are setting the table where anyone can see the same numbers. The language is intentionally calm. Phrases like routine, observations ongoing, and impact probability decreasing are not code. They are the weather of orbit, fitting. And when the language changes to attention, the reason is not vibes. It is a specific threshold crossed by a calculable probability on a particular date. Transparency keeps the grown-up tone intact, even when the internet prefers popcorn. Suppose, for the sake of readiness, that a genuine risk appears on the board for a time far enough in the future to do something about it. The next moves are not mystery movies. You add radar if the object wanders near enough for a ping, because radar shrinks the uncertainty like nothing else. You organize an observing campaign to nail down shape, spin, and likely composition, because those traits matter for how a nudge will work. You run deflection design studies that look at two simple ideas. One idea is to hit the object gently but early, so a small change grows into a miss. The other idea is to push steadily with a slow tug over months, using a spacecraft's gravity or a sustained thruster. None of these require heroics if you start soon. The trick is time. Early action turns a whisper into a mile. What if the timing is not generous? Agencies practice that too, through tabletop exercises where they invent a fake threat and then make the team respond in real time. Who speaks to the public? Who books telescope time? Who calls satellite operators to watch for dust and debris? Who calculates air traffic advisories for a harmless meteor over the ocean? It is all choreographed so that if a real scenario surfaces, muscle memory takes over and the dance begins without tripping on the rug. The most common outcome remains the dullest. The more we look, the less dramatic it gets. That is not failure. That is success. Planetary defense is the art of turning unknowns into yawns. When you hear no threat, you are listening to a system that measured, checked, and chose not to cry wolf. Earth is basically a rock that won the cosmic lottery. And one of the prizes is a network of people whose idea of excitement is watching a probability shrink to nothing. So the next time a headline shouts close pass, translate it to good practice, the hall monitors logged the visitor, erased the chalk rumor from the board, and left a polite note for the next shift. Up next, we let imagination stretch its legs again. If we wanted to meet a fast mover on purpose, could we launch a quick chase? And what kind of spacecraft would make the sprint without spilling the coffee? Chapter 16. Mission Improv. Could we chase it? Imagine the alert hits your desk at dawn. A fast visitor from deep space is already inbound, and the calendar laughs at you. The dream is to meet it out there, take a whiff of its breath, and maybe snap portraits so close you can count the pebbles. The reality is that rockets, like espresso machines, have warm-up time and an attitude. This is Mission Improv, where ideas sprint ahead and the fuel budget grabs them by the collar. The fuel budget is where dreams meet math, and math brings a calculator and a frown. There are a few ways to sprint. The first is the old-school chemical dash. Stack a strong booster and a small, tough probe, then burn like you mean it on the way out of the neighborhood. Chemical engines are the drag racers of spaceflight. Huge shove now, not much patience later. The advantage is simplicity and speed. You can launch in weeks if the hardware already exists, or can be adapted from something on the shelf. The downside is that you pay for every unit of change in speed with propellant mass, and mass is that friend who never pays for dinner. To keep the spacecraft light, instruments must be few and clever, like a camera that doubles as a navigator and a dust counter that moonlights as a thermometer. Option 2 is solar electric propulsion. The marathoner, big solar arrays, thrusters that sip propellant and push gently for months, and a trajectory that spirals outward with calm determination. The shove is small at any moment, but it never stops. By the time you reach the meeting point, you have stacked a surprising amount of speed. The trick is that you have to be on the road early. For a target already halfway to the exit, the patient strategy becomes a chase scene where the hero runs in slow motion. Still, if you hear about the visitor while it is far out, this approach can work, and it buys you the ability to fine-tune the aim on the fly. There is also the stunt driver's move, a solar swing, to bag free energy. You dive toward the sun, burn at closest approach when your engine gets the most return, and fling yourself outward on a higher energy path. It is the spaceflight version of skateboarding, down a steep ramp and kicking at the bottom. The timing must be exquisite, the heat shield must be fearless, and the navigation must thread a narrow window. Do it right, and you leave town with a swagger that chemical push alone could not afford. Do it wrong, and the sun keeps your skateboard. If none of those are fast enough, think piggyback. Maybe a spacecraft already headed sunward or outward has room for a hitchhiker. A small secondary probe tucked into a carrier can wait for the right moment and then peel off into an intercept. It is rideshare with ambition. The catch is that you inherit the parent's schedule and trajectory. You also inherit vibration limits, power interfaces, and a payload bay that was not designed around your whims. Still, the speed you get for free by launching with the parent makes the improvisation worth the hassle. CubeSats add a pocket-sized twist. A briefcase-class chaperone with a tiny engine and a compact sensor suite can be kicked free near the right geometry and sprint the final leg. What can a package that small do? More than you think. A short pass through the coma can scoop dust into aerogel tiles, sniff gas with a micromass spectrometer, and ping the environment for charged particles. The data pipe is narrow, so the CubeSat must be ruthless about compressing and triaging what it sends. Picture a battlefield medic. Take the vital signs, tag the sample, radio the essentials, and accept that this is a one-way trip. Whatever you launch, autonomy is not optional. The target is faint. The geometry changes daily, and light takes minutes to shout instructions across space. The probe has to guide on the comet's glow, reject false stars, dodge dust clumps, and decide when to shutter exposures to avoid blinding itself. It must schedule the instrument ballet so that the dust analyzer breathes at the same time the camera locks focus and the thermal imager catches the warm flank as it spins past. There is no time for committee meetings. The flight computer must be the committee. Sampling strategies come in flavors. A gentle dust collector can fly through the outer coma at a safe distance, where particles are small and the risk is civilized. A braver approach is a skimming pass near the densest glow, trading hazard for richer samples. The bravest is a micro-impactor dropped ahead of the probe. It smacks the surface, lofts a plume, and the main spacecraft sniffs the spray. That last one is spicy in a flyby because you get one shot and the plume does not care about your schedule. Choose wisely. Every instrument competes for mass. A camera with a wide-angle mode to catch the tail and a narrow-angle mode to frame the nucleus. A dust spectrometer to weigh grains and taste their mineral flavor. A gas analyzer to look for water vapor, carbon compounds, and rarer breath that tells you about deeper layers. A magnetometer to sense whether the coma builds a tiny magnetic cocoon. A radiation monitor to track space weather that might complicate the tail's dance. If one device can wear two hats, it goes to the front of the line. Navigation is an arcane art on a schedule like this. You combine star trackers, optical navigation on the target, and Earth-based measurements of the probe's radio tone to back out distance and speed. The operations team then nudges the thrusters in little spurts to slide the aim point by a few dozen kilometers this way or that. The target does not wait. It is like docking with a train that refuses to slow down and insists on reversing the platform every few hours. Cost and schedule are the last bosses. A bespoke top-shelf mission might need years of paperwork, lab testing, and launch queue wrangling. The improv answer is a modular spacecraft bus with instrument slots ready for emergencies, a standing contract for a fast launch, and a shelf of parts that already passed their exams. You will not get perfection. You will get good enough and on time, which in deep space often beats flawless and too late. Could we chase it? Yes. If the alarm rings early, the trajectory is not ridiculous, and we accept that elegance will give way to hustle. The prize is a brief meeting with a messenger from a different star's past, a handful of grains in a collector, a spectrum with character, and images that anchor the story for decades. Next time, we bring the crowd into the control room, how backyard telescopes, public archives, and open code help pin paths, catch outbursts, and turn a global audience into a real part of the discovery. Chapter 17, Citizen Science, and Open Data. How you can follow along. Somewhere right now, a backyard telescope is doing hero work while the cat walks across the keyboard. And honestly, that is the vibe of modern discovery. Interstellar visitors used to be the private party of mountaintop observatories. Now the guest list includes garage domes, school rooftops, and a surprising number of tripods in driveways. The secret sauce is simple. Open alerts tell you where to look, open archives tell you what was already seen, and open software teaches your laptop how to turn faint smudges into useful measurements. Space is big, so is the internet. Let us start with the easiest on-ramp, being the second set of eyes. When a new object is posted to a public watch list, it comes with a provisional path and a request that might as well read, "Please send dots." Those dots are astrometric positions, measured against the starry backdrop. With a modest telescope and a camera, you can collect a short series of images, time-stamped to the second, and feed them through software that matches catalogued stars, solves the field, and finds the visitor's pixel coordinates. A handful of careful positions from different longitudes tightens the predicted path quickly. Your personal reward is small numbers with serious gravitas. The community reward is that tomorrow night's predictions stop wobbling. Photometry is the next rung on the ladder. This is measuring how bright the object appears through a filter and how that brightness changes with time. A simple way to start is differential photometry, which compares the visitor to nearby comparison stars in the same image. Choose well-behaved stars with published magnitudes, measure them and the target with the same circular aperture, and let the ratios cancel out thin clouds and atmospheric mood swings. When many observers in different time zones chain their light curves together, day turns into a continuous night, and rotation hints appear where a single observer would only see a gentle rise or fall. It is group jazz. Your notes fit into a longer melody. Stacking is your superpower when the target is faint. Take many short exposures rather than one long one. Align them on the predicted motion of the object and add them together. The noise averages down, the comet sharpens, and that "I swear, I see it" becomes a clean detection. There is an art to choosing the stack length. Too long, and the object's own motion smears it. Too short, and you leave signal on the table. The happy middle depends on the night's seeing and how fast the visitor slides across the field. Practice on known asteroids, and you will feel the rhythm quickly. Open archives make you a time traveler. Public survey images often go back days or weeks before a discovery announcement. That means the object may already be hiding in the past, faint but present. This is called precovery, and it matters because every night you push the record backward, the path forward tightens. Pull an old frame, search the predicted box, stack a few adjacent exposures if available, and if the smudge pops out, measure it and report with the exact time. A single honest precovery can move the projected corridor on the sky by a dramatic amount. It is like finding an old receipt that settles a bet. Catching outbursts is where amateurs often shine. Professional surveys cover huge swaths of sky, but may not stare at the same spot for long. A backyard observer who revisits the target nightly can spot a sudden brightness jump or a new fan of dust and log it within minutes. If you can, grab a short sequence to show how the coma grows over an hour. Post a preliminary note, then follow up with processed measurements. You're not just saying, "Wow," you're documenting change with a clock. Coordinated campaigns elevate all of this. Join a community where observers share plans, divide time zones, and avoid duplication. Someone in the West may grab the early evening set. Someone in the East catches the dawn. Standardizing filters and exposure times helps stitch the data cleanly. A simple rule keeps the stream trustworthy. Write down what you did and what you changed. If you swapped filters, note it. If clouds wandered through, say so. The cat is allowed to step on the keyboard. The logbook is not allowed to lie. Open code is the quiet MVP. Field solving, centroiding, light curve fitting, and even tail analysis, now live in friendly packages that beginners can learn over a weekend, and veterans can tune like instruments. Many tools can fetch up-to-date star catalogs automatically. correct for distortion, and export the precise formats that the central clearinghouses expect. The result is that quality no longer depends on owning a mountain, depends on patience, calibration, and pressing the right buttons in the right order. Ethics and etiquette matter. Do not rush to dramatic claims. If you think you see a fragment, ask another observer to confirm before you trumpet the news. Share raw frames along with processed versions so others can check your steps. Credit the work of surveys and fellow amateurs whose data you use to build your case. Science is a team sport where the scoreboard is accuracy, not volume, and do not underestimate the value of simply looking. Visual observers still catch weather that cameras miss. A peculiar green tinge, the way a tail bends near a bright star, a fleeting streak that might be a meteor grazing the same field. A short note in a log can prompt images to aim a camera and capture what your eye saw first. Human attention is still a sensor like no other. Plus, you get to say you watched a messenger from another star drift between constellations while the neighborhood sprinklers clicked on. That is a memory worth the midnight chill. The point of all this is empowerment. The tools are out there. The data are public. The sky does not check your degree before it allows photons to fall on your detector. With care and curiosity, you can help refine orbits, reveal rotation, catch outbursts, and write a line in the story that professionals will cite. Earth is basically a rock that won the cosmic lottery. One of the prizes is that anyone under the same sky can help count the coins as they glitter past. Next, we pull the lens all the way back for the finale. Why a single interstellar hello matters in the long arc of our species, how attention turns into understanding, and what chapter we might write the next time a traveler from the deep dark knocks on our door. Chapter 18. The big picture. Why one visitor matters every once in a while. The night throws a pebble at our window. We look up, half expecting to catch a culprit, and instead we meet a traveler with no return address. Whether or not 3IATLAS truly swerved, the rumor itself is a teacher. It reminds us that seeing is a negotiation between nature and our expectations. When the line on a plot seems to bend, we learn to ask whether the bend lives in the object, in our instruments, or in the choreography of our own moving vantage point. Curiosity yanks us toward the telescope. Discipline walks beside us, hands in pockets, whispering, check again. One visitor matters because it forces us to rehearse how knowledge happens. First comes the spark. A faint point appears, and with it, a possibility. Then comes the grind, timestamps, calibrations, cross-checks, and the quiet sport of trying to break your own favorite explanation. Only after the grind earns a few bruises do we get to tell the story out loud. A single interstellar passerby is a microcosm of that arc. It is as if the cosmos handed us a pop quiz, and we discovered the test measures more than memory. It measures patience. It also tests perception. The sky is a three-dimensional stage that we watch from a moving balcony. Our brains love shortcuts, and shortcuts are treacherous when the scenery shifts underfoot. A crooked trace can be a straight path seen at an angle. A steady shove can come from gas you cannot see. A flashy brightening can be a dust cloud playing tricks with the light. Each surprise is not a humiliation, but an upgrade to the way we look. The more we practice this, the less we flinch at the next oddity, and the more comfortable we become with the sentence, here is what we know, and here is what we are still testing. Another reason a single visitor matters is that it gives us a rehearsal for difference. Most of what we study was born under our own star's rules. Interstellar objects carry a different accent. Their chemistry, structure, and behavior arise from nurseries we have never visited. If we want to understand planets everywhere, not just the family next door, we need these wayfarers to stroll past so we can sample, compare, and let our models stretch. Even a negative result, no weirdness here, just ice and dust, shrinks the space where more exotic possibilities can hide. Tightening the ordinary is how we make room for the extraordinary to stand out. it is also a rehearsal for humility in public. The world hears the word swerve and imagines swagger. Scientists hear it and picture residuals refusing to sit still. When we explain that the exciting rumor softened after better data arrived, we are not backpedaling, we are modeling how grown-ups change their minds. The tone matters. Say, we learned something new, not, never mind. Doing this with grace builds trust for the day when the news does not soften, when the headline turns into a real anomaly, and we need the whole planet to lean closer. One traveler activates a network. Professional surveys widen their cadence. Small observatories volunteer nights. Hobbyists stack images in living rooms. Data engineers polish code that can fold new measurements into predictions before breakfast. That ecosystem is not background noise. It is the living infrastructure of discovery. A stranger from between the stars shows up, and suddenly thousands of people separated by oceans are all pointing at the same speck, speaking a shared language of timestamps and angles. If you ever want a portrait of how modern knowledge is made, watch that dance in Fast Forward. A guest like this also sharpens our sense of readiness. It asks whether we could meet a fast object in the dark, whether we have hardware we can launch quickly, whether our analysis pipelines are sturdy enough to separate physics from phantom. Each test nudges agencies and labs to keep a kit on the shelf, instruments that can fly on short notice, software that handles edge cases gracefully, playbooks that turn a late-night alert into action without panic. A lone emissary is not just a research target. It is a drill. And yes, there is the delicious, careful whisper of what if. Entertaining, engineered scenarios is not gullibility. It is good hygiene for imagination. The point is not to leap. It is to know what signs would justify leaping, and to make those signs so specific that they can be hunted honestly. If a visitor ever does behave as if someone built it, we will need practice separating delight from confirmation. The only way to do that is to rehearse now, when the likely answer is natural and the stakes are merely intellectual. Finally, one visitor matters because it rearranges our sense of home. It tells us the galaxy is not a silent painting, but a place with traffic. The very fact that a speck from another star system can stumble into our skies, be recognized by people who had dinner 30 minutes earlier, and have its breath analyzed before dawn, that is civilization leveling up. We are not only building bigger mirrors and faster chips, we are building a culture that treats mystery as an invitation rather than a threat. So when the story of 3I/Atlas fades into the logbooks, it will leave behind more than a path on a chart. It will leave better habits, sharper tools, and a community that knows how to hold excitement in one hand and skepticism in the other without dropping either. The next knock at the window will find us more ready, more curious, and, let us be honest, just as giddy. Next time, we will get specific about a favorite fork in the road, how to tell a natural light sail lookalike from a deliberately engineered sail, and what the very first sentence of a reply from Earth should be if we ever catch someone surfing starlight on purpose.